Another thing I should ask you about, not only since you've already brought it up and given me permission to do so, but because it's of enduring general interest and also metaphysical interest, is about the history of locality as a phenomenon in physics.
So this is something else I may ramble for a
I
while about.
really love the rambling. That's great.
Cut me off when you need to. So look, there's a really interesting story here. Um, you know, there's a very basic expectation. There's a very basic intuition with which we approach the world. Okay, this intuition is much, much older than um, modern physics or modern science. By modern, I mean since the 17th century. It's much older than that. It's much older than scientific speculation. It's probably much older than human beings. Okay, it seems to me that fish have this intuition, or octopi have this intuition, or something like that.
Well, you never know about octopi.
Yeah, here's the intuition, um, which is called nowadays locality in physics. The intuition is that things that happen here, okay, are only, or let me put it this way. Things that happen here only directly and unmediatedly influence other things that happen immediately contiguous to here, both spatially and temporal. Okay. The effects of stuff that go on here don't jump discontinuously across space and time and affect something else. Okay. Things that happen here only directly affect other things that happen immediately contiguous to them. Of course, by doing something here, I can make it the case that eventually dramatic things happen far away. I give someone an order to travel to Chicago and punch somebody in the face, or something like that. Or I flip a light switch over here, and on the other side of the room, a light goes on. But in all of those cases, we are convinced that if you scrutinize the process carefully enough, if you rip up the wall where the light switch is, you'll find a wire running continuously and without a break all the way from the light switch to the light that went on. If I analyze the process by which the guy in Chicago got punched in the nose, well, I affected this guy while he was standing right next to me by giving him this order. I can even break that down. I influenced the air right at my lips by moving my lips. That moving air, caused air next to it to move. That moving air caused the air next to it to move, dot, 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 until it got to his ears. Then he goes and gets on a plane, keeping my orders in mind all the time, travels to Chicago. The guy ends up getting punched in the nose. Okay? The claim is that under any circumstances where something that happens over here affects something that happens over here, it will always be possible to find, by sufficiently rigorous examination, an unbroken chain of mediating causes and effects and causes and effects and causes and effects that stretches without a break all the way across the spatial and temporal influence from the first cause to the ultimate effect. Okay, from my flipping the light switch to the light going on, from my moving my lips in a certain way to a guy getting punched in the nose in Chicago, blah, blah, blah. Good. As I say, this is a very, very deep intuition that with which we come to the world. It seems to me it's an intuition which in some crude form is hardwired into us by natural selection. Okay, it's not a joke that it predates human beings. It's not a joke to say that fish and lions and so on believe in locality. Okay. If the predator is far away, he can't hurt you until he's near you. Okay. And indeed, violations of locality, okay, are very much of the essence of what of what we have in mind when we use words like magic. Okay, voodoo is supposed to be, it's part of the essence of voodoo that it's supposed to be a genuine violation of locality. Okay?
I never made that connection.
You
Interesting.
stick pins in a doll's stomach over here, and it's not thought that that gives the guy a stomach ache on the other side of town because it generates waves, physical waves of anything going out. It's magic, okay? And it's magic, it's part of the essence of what you have in mind by calling it magic, that it violates locality, okay? So, locality is a word that's sometimes associated with special relativity, with the constraints of special relativity, that no influences can move faster than light. That altogether misses the depth of what's going on here. This is a very deep, primordial, pre-scientific, pre-human, hardwired by natural selection intuition we have about how the world works and about what can be expected from the world and its reactions to what I do. Good. Or to what any agent does. Good. This principle has a really interesting history in modern physics, where, once again, what I mean by modern is the developments starting with figures like Galileo and Newton and so on in the 17th century. Specifically, when Newton first wrote down his theory of gravitation, it explicitly violates this principle of locality, okay? It says that two material bodies at a certain distance from one another will exert a certain gravitational force on one another, okay? And moreover, if you move one of them, the gravitational force that the other will experience will change instantaneously, and it'll change without any physical process that you might refer to as propagation of that influence, changing in the space between them. Okay?
If the sun vanishes, we fly away immediately.
And the sun vanishes, we immediately fly away. Okay? Good. It was widely noticed as soon as it was written down that Newton's universal law of gravitation was a violation of the principle of locality. And lots of people, this kind of violation was referred to in the nomenclature of that time as action at a distance. Okay, Newton's universal law of gravitation was said to stipulate that there was an action at a distance from one mass to another, and lots of Newton's contemporaries, not least Newton himself, considered it for that reason preposterous. Okay. And Newton was the first to say, and he shows this by standing on his head and working very hard during his career to try to imagine a local account of gravitation, which he was never able to do. But everybody, including Newton, reacted to this by saying, look, this is great. This is providing a wonderful account of the motions of the planets and so on and so forth. But it couldn't be the final account of gravitation. And the reason that it couldn't be the final account of gravitation was precisely its violation of this very deep principle, this very deep primordial expectation we have of the world, that it's going to be local. Good. So that's where things stood for a couple of hundred years. Okay. There was this Newtonian law of gravitation. Everybody knew it was non-local. Everybody knew it was of fantastic predictive and explanatory utility. Okay. But I don't know if everybody, I don't know the history well enough. Certainly lots of people were very vocally skeptical that it could possibly be the most fundamental account of gravitational phenomena, precisely because it was non-local. Good. Nothing happens about this for 200 years. Then, in the 19th century, people started making systematic scientific investigations of electrical and magnetic phenomena. And the laws that were written down, particularly for electrostatic attraction and repulsion between like electrical charges or different electrical charges, had exactly the same mathematical form and exactly the same predictive and explanatory utility as Newton's law of gravitation. Okay, the force that electric charges exerted on one another, according to 19th century mathematical theories of electrostatic force, were non-local in exactly the way Newton's gravitational force was non-local. But the interesting thing about electricity was it was a more complicated case than gravitation, because early experiments by people like Faraday showed that there was some intimate connection between the electrical force and the magnetic force. People started trying to develop a unified theory of the two of them. And these developments went on at a frenzied pace. There were lots of brilliant people working on this, especially, some names that are especially important are Faraday and Maxwell. And this development culminates toward the end of the 19th century in Maxwell's equations. The first thing to say about these equations is early in the 19th century, when people were studying forces between electrically charged particles, people started to get into the habit, initially as a purely notational device, to talk about things that they called electric fields. Okay. So they would speak, but this was just a notational matter. They would speak not as if this charged particle exerted a force on this charged particle, but rather this charged particle created around it an electric field that extended throughout all space. And that field was what was directly felt by the other charged particle. Adopting this notation makes the phenomenon look more local, okay, on a sort of formal level, on a sort of mathematical level. Nobody at the time took that seriously. Nobody at the time was taken in by that, okay? Everyone was convinced that there was still a very deep metaphysical puzzle here about an apparent violation of locality. But this field language, this field notation began to insinuate itself into the way people talked about electric and magnetic phenomena. And by the time you get to Maxwell, a big transformation has taken place. Maxwell is trying to put together all that's been learned over the previous century about electrical phenomena and magnetic phenomena and their empirically discovered relationship to one another. And the equations, the four simple equations that Maxwell is forced to write down in order to bring all these phenomena together, ends up treating fields as basic ontological constituents of the world on a metaphysical par with material particles. Okay, fields turn out to be the kind of thing that can push one another around. They have their own rich internal dynamics. It turns out that, for example, if you just look at the energies of particles interacting with one another electrically, and they're flying around and having all kinds of effects on one another, if you just keep track of the energies of the particles, the total energy of the system you're looking at won't be conserved. It won't be the same at different times. The same is true of momentum. But it was discovered by various investigators that if you attributed certain amounts of energy and momentum to the electric and magnetic fields, by means of a very simple formula, then you could prove that the total energy of the system consisting of the particles and the fields was conserved. So there was reason to believe that electric and magnetic fields, these things that had just been taken as notational devices 50 years earlier on, were now things that there were strong reasons to imagine could have energy, could have momentum. Once again, they contained a rich internal dynamics. They were pushing and pulling on one another, so on and so forth. They were acting more and more and more as if they were genuine, fundamental, physical stuff as well, okay? And one of the great revolutions in our picture of the world that we get to by the end of the 19th century, with Maxwell having written down his equations, is that the fundamental ontology, physical ontology of the world has suddenly doubled. Okay, it once consisted just of material particles. By the end of the 19th century, almost everybody is convinced that it consists of two kinds of things: material particles and electromagnetic fields. Okay, and that the fields are completely on a metaphysical and ontological par with the particles. Okay. Another thing that happened, a beautiful byproduct of this, okay, was that it was noticed that if you actually solve Maxwell's equations carefully, if you have, say, two repelling positive charges here and here, and you ask what happens to the force on this charge if I suddenly move this one, it is not the case that the force on this charge instantaneously changes. It's the case that moving this one changes the electric field in its immediate vicinity. That change in the electric field in its immediate vicinity changes the electric field slightly farther away. That change in turn changes the electric field slightly farther away than that, ... This change ripples across space at what turns out to be the speed of light. Okay, and after a finite time, results in a change in the force experienced by this other particle. Moreover, the process of propagation of this change throughout the spatial interval, okay, is something which has measurable physical manifestations. It's indeed electromagnetic radiation. It's light, okay, is a sort of little light flash propagated from one to another. You can see, if you put the appropriate instruments in there, the change in the force propagating at a definite finite speed, the speed of light, from the particle that's generating the field to the particle that's fielding the field. Okay, so at least insofar as electromagnetic phenomena is concerned, the threat of violations of locality has collapsed. Okay, good. People like Einstein were enormously inspired by this Maxwellian account of electromagnetic behavior, and engaged for a whole bunch of reasons, but one of them were these concerns about locality, in trying to understand the phenomenon of gravitation, okay, more after the model of Maxwell's treatment of electromagnetic phenomena. And the result of this is one of, what's universally regarded as one of the greatest achievements of the human imagination. In 1915, when Einstein first publishes his so-called general theory of relativity, which is a theory of gravitation. And lo and behold, one of the many astonishing accomplishments of this theory is that Newtonian mechanics is rendered local. Okay, that is, gravitation is rendered local. That is, it turns out in Einstein's general theory of relativity, just as in the Maxwellian case, that if I move one of these masses, it changes the gravitational field, or what is now the geometry of space-time in general relativity, only in the region immediately next to it. Those changes cause changes further out. Those changes cause changes further out, ... And once again, this propagates through space at the speed of light, okay? And it's only after a finite time that the other mass feels the change. This phenomenon of propagation, which you should also in principle be able to measure, okay, is called a gravitational wave, okay? And lo and behold, just a couple of years ago, people won a Nobel Prize for finally directly observing these gravitational waves that Einstein's theory had predicted. So this is a sort of beautiful, immensely satisfying story, okay? Everybody had to hold their breath for 300 years, okay? But they held their breath for 300 years and they were rewarded, okay? The initial crisis caused by Newton's universal law of gravitation gets beautifully, satisfyingly, breathtakingly resolved in Einstein's general theory of relativity. And lo and behold, in the 2020s, people actually, for the first time, are able to observe these gravitational waves that propagate the changes in these forces through space-time. So this is a beautiful story. Unfortunately, a few years after general relativity, with the advent of quantum mechanics, this blows up in everybody's face, okay? Quantum mechanics, and this is what makes the story so poignant and so dramatic and so shocking. It turns out that the quantum mechanical recipe for making predictions about the outcomes of experiments includes instructions which, at least on the formal level, you'd be tempted to call non-local, okay? That is, the recipe that you're supposed to follow instructs you in certain circumstances that when you measure some feature of a particle over here, depending on how that measurement comes out, you ought to instantaneously change the way you describe in your formalism the state of some particle over here, which may be arbitrarily distant, which may be on the other side of the universe, okay? Good. Nobody in the early days of quantum mechanics, it was Einstein who first noticed that quantum mechanics contains these instructions which are non-local, okay? The way the algorithm was initially written down, you have to do some digging in the algorithm to really expose the fact that it's giving you non-local instructions about how you ought to proceed. It was Einstein in his famous paper with Podolsky and Rosen, the so-called EPR paper in 1935, I think, who first very clearly points out that the formalism is non-local in this way. And this is a particularly emotional matter for Einstein because he just got finished saving the world after, 300 years from Newtonian non-locality, okay? So Einstein and his colleagues notice that there's this non-local feature of quantum mechanics. Of course, Bohr's, if you want to read Bohr's most sustained written account of his philosophical attitude towards quantum mechanics, you can find it in his famous response to this EPR paper, okay? The EPR paper is, Can the Quantum Mechanical Description of the World be Considered Complete? And Bohr, several months later, publishes a paper with the same title that's intended to dismiss Einstein's concerns. So Einstein notes that the algorithm contains this non-local feature, okay? And he considers that weird and alarming and an indication that something we don't understand, that this couldn't be the end of the story, just as Newton's non-local theory couldn't have been the end of the story. Okay. And Bohr essentially writes a paper. I mean, it's a paper that's very, very hard to understand. I've heard a story from friends of mine, just as a little sidelight, but it gives you an indication of how difficult Bohr's response was to understand. I've heard recently that almost all of the reprintings of Bohr's paper that have been published over the past 60 years had two of the pages reversed. Okay. And nobody seems to have noticed. Okay. This is how impenetrable this paper is. Okay. You look at it, it's really hard to understand. But if somebody holds a gun to my head and says, tell me in one sentence what this paper is saying, I take it the thing that Bohr is saying is, who gives a shit about this non-locality? That we make no pretense to describing the world here. Okay, this is not the fact that the algorithm for making predictions contains this non-local instruction shouldn't be construed as our saying the world is non-local. We are not saying the world is non-local. We're not saying the world is local. We're not saying the world is anything. We are not in the business of saying how the world is. We're in the business of telling you how to predict the outcomes of experiments. Who cares about this? Why is Einstein all worked up and mired in these old-fashioned questions about what's really going on in the world? We've outgrown questions of what's really going on in the world. We're so over questions about what's really going on in the world, so on and so forth. Bohr has a lot to say in this paper. A lot of it is very hard to understand. But like I say, if you hold a gun to my head and ask me for the one sentence summary of what Bohr is saying, that's what Bohr is saying. Good. The issue lies there. I mean, astonishingly, when Einstein published his paper, everybody in physics got very worried. Oh my God, Einstein has an objection to quantum mechanics. What are we going to do? Bohr publishes this pile of gibberish a couple of months later, which is in no way a response to anything, okay? And everybody says, thank God Bohr solved the problem. And I can testify to you that generations later, if you go to your physics professor as an undergraduate, okay, and say, what about these Einstein objections to quantum mechanics? Your physics professor, at least when I was an undergraduate, and it certainly continued for at least a generation or so after I was an undergraduate, your physics professor would tell you, what's wrong with you? What are you in junior high school? Bohr cleared that up a long time ago. Go read Bohr's paper. And if you say to your physics professor, can you just tell me what Bohr said to clear it up? The guy says, yeah, I can't remember. I don't know, but I know that Bohr cleared it up. Go read Bohr's paper. It's all over. Okay. And you go read Bohr's paper, and it is literally like listening to the oracle at Delphi. Okay. It's like listening to somebody hanging upside down by their ankles, screaming hysterically, and you're supposed to understand deep wisdom in this. Okay. Good. So Einstein said, something's wrong here. This is non-local. Okay. Then another 30 years goes by where nobody says anything. Nobody says anything because everybody has been told that Bohr settled this problem. Okay. Even though on being asked, everybody found that they weren't able to say how Bohr, it's like what Augustine famously says about time, that you know exactly what it is until somebody asks you. Okay. So this is true of Bohr's response to EPR. You know exactly what it is until somebody asks you. Then you get all confused and you tell the student to go read Bohr's paper. And it turns out that doesn't help. Good. Finally, Bell comes along in the mid-60s. In the mid-1960s, sees that the EPR argument is correct, okay, wonders is also aware, as very few people were aware at the time, of this attempt by David Bohm to solve the measurement problem, okay, to write down an explicit version of quantum mechanics which was capable of being treated as a universal theory, something that also solves the measurement problem, treats the observer like an ordinary physical object, blah, blah, blah. He was aware of Bohm's theory. He was aware that Bohm's theory was non-local in just the way that Einstein observed that the standard quantum mechanical recipe was non-local. And Bell wondered whether you could improve on Bohm's theory by writing down another theory which was as successful as Bohm's theory and as quantum mechanics in making correct empirical predictions, but was rid of this disease of non-locality, just as Maxwell had done for electromagnetism, just as Einstein had done for gravitation. And there was a tremendous temptation to say, when confronted with an apparent non-locality in the world, don't worry, don't get hysterical. We've been through this before, twice, okay? We've been through this with Newton. We've been through this with electricity. They all looked non-local at first. It turns out you think harder, you hold your breath for 300 years, everything gets cleared up, okay? Good. Bell fiddled around with Bohm's theory for a while, trying to come up with a local version of it that was as successful at making correct experimental predictions, found he couldn't do it, okay, and then realized that there was a simple argument, an astonishingly simple argument that takes 15 minutes to present, and we now have even cleaner versions of it that take 5 minutes to present. Found he could construct a proof that there could be, that any theory that made the same predictions about these pairs of particles as quantum mechanics did, like Bohm's theory or anything else, must include at some point or another one of these non-local instructions, okay? The non-locality was inescapable. Okay, so we now had a simple proof that what had come to, that the way we had been saved in the case of gravitation, that the way we had been saved in the case of electricity was not going to happen in this quantum mechanical case, okay? That this non-locality was not a sort of disposable artifact of the mathematical formalism or part of an approximate description of what was going on. It was absolutely, as a matter of mathematical certainty, as a matter of mathematical proof, inescapable, okay? And this is one of the great metaphysical challenges of quantum mechanics, okay? Once again, you have a Bohrian kind of approach. You have a radically instrumentalist kind of approach. You couldn't care less about non-locality. The recipe for making predictions contains non-local instructions. Who cares? And if you say, well, I don't understand, isn't that asserting that the world is non-local? Answer, from Bohr's perspective, not at all, not in the slightest. You seem to think that science is in the business of telling us how the world is. It's not. Get over it. Get that out of your head, okay? That's not what's going on. But the minute you try to entertain what we're being told as claims about the way the world is, we have a proof from Bell that that this non-locality is going to become a genuine claim about the world out there behaving non-locally. Okay. And this, I think in one of Brian Greene's books, and I wouldn't dispute this, Brian Greene refers to this particular discovery as the most startling single discovery in the history of natural science. Okay. And it really does. And this discovery was famously referred to by Abner Shimoni, a great philosopher of physics of a previous generation, as what he called experimental metaphysics. Okay. This seems to be bearing on really deep claims about the structure of the world, claims which I've just explained in my ridiculously long story, claims that are deeper than almost any other commitments of modern science, claims that are older than modern science, claims that surely cavemen believed, claims that it seems reasonable to me to say fish believe and octopuses believe, and so on and so forth. So that's that field. And that's why this issue of Bell's theorem, this issue of non-locality, is a huge, is an enormous example of how if we're licensed again to begin to take physics realistically, how modern physics might have very, very profound and surprising implications about our ideas of the basic metaphysical structure of the world and of our ideas about time and space and so on and so forth.